How do you solve question C? 5 over x minus 1. We want to find the inverse. What's the idea? Zakia, very good. Who? Wonderful. Kirill, great. And Lisha, very good. All right, guys, what's the idea of the inverse? Very simple idea. Okay, Jacqueline, great. 1, 2, 3, 4, 5. I have, at the moment, 25 students here. Should be more solutions. And they should be fast. All right. Let's look at C. The idea is I can set y equal to f inverse of x. And when I put y as the input of the function f, they cancel each other so that I have simply the input x. 5 over y minus 1 is x. And then it's just basic algebra. Then what you can do is you can multiply by y minus 1 and divide by x. So you will get your solution this way. Good. So it should be either 5 over x plus 1, or you can write it as x plus 5 over x. Both are correct. Everybody understands how I go through those steps? So as I'm going to move on, any questions? Good. So for D, it's just the cube root of x. Let's look at E. So we set y equal to f inverse x. And then we have an infinity to do the function. We have that y minus 1 over y plus 1 equals to x. Then what I do is y plus 1 minus 2 over y plus 1. Why do I do this? Is that I look at the numerator and denominator and I see 2 copies of y. And I would be very glad if I could cancel everything out. Yes? So what I want to see is y plus 1, but I see y minus 1, so I compensate by subtracting 2. So y plus 1 minus 2 over y plus 1 equals to 1 minus 2 y plus 1. Yes? And that's supposed to equal to x. Now you see what I achieved here? I had 2 instances of y. Now I have only 1 instance of y. Now everything else is basic algebra. I can move the minus 2 over y plus 1 to the right and move the x to the left. So I have 1 minus x is 2 over y plus 1. I take reciprocals and I have y plus 1 equal to 2 over 1 minus x. And that makes y equal to 2 over 1 minus x minus 1. And simplifying, I can write it as 1 plus x, 1 minus x. Is this clear? So, yes, I hope it should be clear. That's still a review. So now I'm gonna yes, and then what's the last question here that I asked? It's question number F. Please solve question number F and I will be with you shortly. All right, guys, are you ready? I still do not see solutions for question number F. Okay, Hu, thank you. Thank you, Leiki. Lisha, thank you. Okay, Khalid. Thank you. Somebody managed to escape us. Okay, so let's solve this question and move on to better and one more interesting things. So here is the situation. Again, you set y equal to the inverse. Plug the inverse, you get y to the 5 minus 2 over y to the 5 minus 7. And because it's the inverse, you get the initial input x. Yes? And then you would like to see a one instance of y rather than two. So you might write y to the 5 minus 7. And you add 5 because you only had a minus 2 here. Yes? Because you have a minus 2 on the top, I add 5. Everybody understands why I write y to the 5 minus 7? Ahoy there. Yes, because of the denominator. And by doing so, I can look at it. You see, I had 2 instances of y. Now I have 1 instance of y. That makes things somewhat simpler. Good. So then I divide and I have 1 plus 5 over y to the 5 minus 7 equals to x. And from there on, it's algebra, basic algebra. And you get y equal to the fifth root of 7x minus 2 over x minus 1. All right, so now let's talk about something very important and a bit more difficult. So from the geometric point of view, from the So you can actually see both the function and its inverse. Okay, so here is a graph, and just any graph that's an invertible function. And if you walk along the x-axis and look up, let's say you see x, f of x is the graph that you're seeing. You follow? X, f of x. Now, if I were to walk on the y-axis and this were my horizontal line, what will I be seeing? If this is my horizontal line, look at it. Then for any y, the function here is f inverse y. Do you understand? X equal to f inverse y. If I if this guy walking on the y-axis looks up, he sees x equal to f inverse y. So actually the same graph captures both. Do you understand? I need your confirmation, or you need more elaboration for this part. An important idea. Do you understand it? All right. Look at it again, guys. You are seeing the same graph. Let me draw, for example, so that you would see it a bit easier. Suppose that we have y equal to x squared, right? Y equals to x squared. What is roughly the inverse function? Can you tell me, please? What's the inverse of y equal to x squared? What do you expect the function to cancel the square? Square root. Exactly, it's the square root. Now let me draw only a portion of it, right? So let me draw, this is the y-axis, this is the x-axis, and let's say when I say y equals x squared, I'm only considering the positive x. So what is y equals to x squared? That's nothing more than the points x squared. Are you still with me? Yes. Yes, okay. Do you understand and what does it mean? Again, I don't want you to see x. It means that the second coordinate is the square of the first, okay? Now a person, and so that's what this person is seeing. This person looking up is saying, well, I am at this coordinate, and the vertical coordinate, this coordinate here, is the square. Yes? Now, if I see a person standing here, or sitting here, and he is sitting in some position y, and he looks up. This is his up, right? What is this coordinate that he will see? Would anybody tell me what is the coordinate that he will see in terms of this coordinate y? In terms of this coordinate, what will he infer to be the altitude of the curve, which is on the x-axis? You see, what is y equals x squared? Again, it means that this guy is standing on the x-axis at some position, some number. He always notices this rule, that wherever he stands on the x-axis, the altitude for him looks like it's the square of the position on the x-axis. Exactly, square root of y. So this guy, for him, the altitude is the x-axis. So sitting on the y-axis at some position here on the y-axis at some coordinate, he infers that the altitude is the square root, right? Because this guy would have known that this is the square. So that's you would know that this altitude, this y, is the square of this number. So this number is the square root. Do you follow? So the inverses are seen on the same picture. Here is what happens more generally. More generally, here is any typical function, x, f of x, right? So that's what a person walking on the x-axis infers to be the altitude. At any position x, the altitude is f of x. Now, a person on the y-axis infers that any position y is such that the altitude is mapped into it. So that's the inverse of y. You see, x equal to inverse y. Why? Because it is the point that when plugged into the function for the horizontal guy would look like y. You follow? Because another, it's just a bit difference between passive and active. Let me again draw something for you. So here he is this guy, right? Let's say I look at this position. Let's consider this position y. Now, what is that position? That position is here. It's x. What's true about x? It's true that f of x equals to y, which means that if I apply f inverses to both sides, f inverse of fx, that would give me x. You agree? But f inverse fx will be, because of this equality, f inverse y. So that's why the guy standing at this position on the y-axis at coordinate y sees the inverse function. Is this clear? I want you to confirm if you understood. It's a matter of passive versus active tense. Similar idea, right? I can say I will do the work, or the work will be done by me. It's a very similar idea here. Just I'm talking about the same thing, but emphasizing, let's say, either the y-axis first or the x-axis first. It does feel very quiet. I'm thinking, what happens to you? My God, do you see that? Same thing I did for the square root of. Good. That's very useful thinking, because you understand, if from the geometric point of view, the inverse function and the original function are kind of together on the graph. They are very linked. They have the same properties. I'll show you that they do. Okay, so clear. Let's continue. So this is what it means. So I can, if I have the graph of f, I can easily visualize the graph of the inverse. So here is the graph of f. Look at it. I marked the dots here, right? The graph of f. Now what happens is that what I want to swap, I want to swap vertical and horizontal, right? So I will rotate by 90 degrees, and now the vertical in the first picture is the horizontal of the second picture. Yes. But the only thing is that this coordinate system, it's kind of this. This is what happens here. In this coordinate system, this used to be, it used to be up and to the right. But here it is now, this is where it rotated. And the x-axis should be was opening to the right, and now instead of opening up, it opens down, right? Normally you present the coordinate system where the vertical opens up, the arrow is pointing up. Do you understand? So by rotating by 90 degrees, I have the graph of the inverse, but it looks, as the Germans say, komisch. It looks very strange. The upward sense is down, like I drew in the picture. Yes. So what do? I take the picture and I flip it I basically take it up and I flip it. I reflect it in the x-axis. Right. So that now, nice to see you, Alex. Right now, the blue arrow points this way, and the red arrow points the original supposed way. Right. So because I want horizontal to be to the right and up to be directed this way. You all understand? So I was able to very simply produce the graph of the inverse by just by very simple motions. Draw the picture on a transparent piece of paper, rotate by 90 degrees, and flip, reflect through the horizontal, flip it over. And you have the graph of the inverse. Here I drew it up, okay? Another way, of course, to see that is the entire motion can be accomplished by rotating along the line y equals to x. Why? Because the coordinates of y equals x. You see, so what happens when I do that reflection? You can see that this position of the x-axis is swapped with this position on the y-axis. So that's the interchange that I want. Okay, this point will be reflected here. This point will be reflected here. The x will be pointing up. The y will be pointing to the right. So it's the same thing as rotating in the line y equals x. Now that is very useful in figuring out derivatives of inverse functions. Yes. Here is a question. So we have astronauts A and astronaut B are doing the spacewalk, and let's try to think what happens here. Astronaut on the x-axis, when he looks up, he recognizes the function y equals x squared at point 3, right? He stands at point 3 and he recognizes that in general it's an x squared, and he's calculating the slope of the tangent line. Pay attention, guys. So this is a tangent line. Now, they agree that the same line is a tangent line, right? So both astronauts on the y-axis, on the x-axis, they see the same line that approximates the curve. So they both agree it's a tangent line. Will they agree on the slope of this line? Will this astronaut and that astronaut measure the same slope when they are looking at this line? Please let me know in the comments. Steven says yes. Alexa says yes. What about the rest of you? What do you think? Will they agree on their measurement of slope? Guys, you're imagining what happens here, right? So I have many nightmares, of course, much worse than yours, right? Where I am flying through a manifold and I'm trying to keep my orientation. And I can show you what manifolds are like. Scary, right? But here it's a very simple curve. So you're walking there. And what does it mean to recognize that this is y equals x squared? Nothing more than to say that wherever the astronaut on the x-axis stands, the other coordinate is the square of the first coordinate. So if he stands at 3, the altitude is 9. If he stands at 2, the altitude is 4. Yes, so understand what is y equals x squared? It's just a relationship between altitude and position on this axis. Good. Now they look at the same curve. Will they agree on the same information? Because for him, position on the horizontal axis for the second astronaut, right? If he's standing at 9, he thinks the altitude is actually 3. This one stands at 3, thinks the altitude is 9. This one stands at 9, thinks the altitude is 3. Do you agree? They don't agree on what is the altitude. They have different notions of altitude. Yes? But they see that this curve has a tangent line. Like over here, there is a tangent line. And this guy can measure the slope and this guy can try to measure a slope. Will they agree on the slope of that tangent line? They see the same line, right? They see that it touches the curve, so you can say they see the same tangent line. Do they agree on its slope? So Irvin says no, Ying says no, Dragon says no. Now, I want us to hear from more of you guys. Khalid said no. Okay, good, interesting, right? So would they agree on, and think about it very simply. Will they agree on the slope for this line? What is slope? Slope is rise divided by run, or in other words, vertical displacement divided by horizontal displacement. Yes, Christian, exactly, right? So the answer is that, of course, they will not agree on the slope in general because they have a different notion of what's horizontal and what's vertical, right? So this one, if there is a dy dx, for this one, dx, the green thing, the green segment is the horizontal displacement. The red segment is the vertical displacement, right? So he will calculate what will be the slope that this guy calculates. This guy calculates slope dy dx, right? But for this guy, the y-axis is horizontal, yes? So what slope will he calculate? He will calculate the slope dx over dy. Because for him, dx is the vertical and dy is the horizontal. You see, I drew two versions of it, right? So for him, dx is the vertical and dy is the horizontal. So what is the differences? Look at it, dx over dy is nothing more than 1 over dy dx. Do you agree? It's inverted, it's 1 over. So so one will measure the slope m, the other one will measure the slope 1 over m. It will their product of their slopes will equal to 1. If you multiply the slope calculated by this guy by the slope calculated by the other guy, you get 1. Do you agree? If, of course, the slope, if the line is not horizontal, if there is a horizontal tangent line relative to this guy, the other guy will say it has no slope because for him it would look like a vertical line. Do you understand? And that's why when you study differential geometry or you go on in Calc 3, you don't consider derivative to be the slope because it's a bit arbitrary. Derivative, you would actually make it into a tangent line. You understand? Because the tangent line, no matter how you look at it, it's the same line. But slope is very arbitrary. It depends on the coordinates that I decided to place on this system. You understand? There is a line, one line, but I can place my coordinate system, and depending on where I place my coordinate system, I will measure different slopes. Do you understand what I'm saying? You don't have to think of it this way in our class. We can say derivative is the slope of the tangent line, but that's very limiting. Do you agree? Because I can make coordinates. I can make a coordinate system like this. I can make a coordinate system like this. I can twist it around. And based on how I place my coordinate system, I will create different notions of horizontal and vertical, and therefore different notions of slope. Right? I can make a line have slope equal to 0 by making my notion of horizontal parallel to that line. Yes? I can make the line not have a slope because I can make the vertical of my coordinate system parallel to the line. Yes, so there is essentially, for a differential geometer, there is only one line because I can just shift the coordinate system, right? There is only one line, and for that one line, we'll have all the slopes. Anyhow, clear? So let's try to understand what slopes will be measured here by each individual. So if this is y equals to x squared, if he sees y equals to x squared, the other guy sees root of y. Do you agree? He sees that altitude x is equal to root of the vertical coordinate. You see what I mean? It's like the difference between passive tense and active tense, right? This one is saying square the first coordinate to obtain the second coordinate. This one is saying take the root of the second coordinate to obtain the first coordinate. You understand that we're talking about the same pairing, but I am see why I mean passive voice. I can say I am giving you an exam, right? So I give you an exam, or you can say the exam is given by me. So that's like changing emphasis between first coordinate and second coordinate first, right? You understand what I mean? That's when people say math is a language. It's kind of, this is the analogies that you might kind of draw when you say it's a language. It's if you understand things like that in a language, you can understand same things in mathematics. So you understand. So this guy can calculate the derivative of x squared at 3, which will be 3 times 2. Yes, so it's 6. This will calculate slope 6, and this one will calculate the slope at 9 to be what? What will be the slope this guy calculates at 9? This one, because we know how to differentiate x squared at 3, it will be 2 times 3, which is 6. And this guy will calculate slope equal to, careful, this one will calculate the slope equal to 2 times 3. And this guy will calculate slope equal to 1 over 6, Khalid, exactly. 1 over 6. It's the reciprocal, because all the difference, they are measuring, there are two coordinates of the same point, and they have the same dx dy. Except for this guy, dy is the horizontal, dx is the vertical. So you just take this derivative and take 1 over it, and you get the slope that was calculated by this guy. So the idea is that it's very easy to calculate derivatives for the inverse function. Do you understand? We will do it in two ways. I will do it abstractly, but I'm trying to show you geometrically as well why it's so easy to figure out the derivative of an inverse function if I know the derivative of the original function. Here is that calculation, okay? dy dx is the derivative of x squared at 3, which is 6. But b is watching the same line, just he has inverted notions of horizontal and vertical. So he sees dx dy, which is 1 over dy dx, which is 1 over 6. Good? So here is the situation in general. If I just have any invertible curve whatsoever, and I have this relationship, I have that there is the point AB on the graph. A and B are on the graph. Calculating the derivative at A, it will be dy dx, it will be some f prime, right? F prime of A. And calculating the derivative at B, it would be 1 over f prime at A, but A is the same as f inverse B. Do you understand what I mean? So look carefully, guys. I said A, B, maybe that confuses you, right? B and A are on the same graph. So I can say B is, let me clear it. B is f of A. Yes, f of A is equal to B. And if the function is invertible, then I can do this. I can say f inverse of fa, that would equal to clearly A, right? But that equals to f inverse B, because f of A, this thing is B. Are you with me? So if I say f maps A to B, it's the same as saying f inverse maps B to A. Please confirm if you understand what I'm saying. Hopefully you're not too confused by the A-B stuff. Basic logic here. If A is mapped by the function f to B, then B is mapped by the function f inverse to A. Do you understand me? Yes, I hope it does. So you see, guys, one thing is you should, and many of you are not doing it, you might understand it when I say that, but can you explain it to somebody? You can try explaining to me at some point, right? Talk, you know, here is what people don't do. They don't talk. And sometimes they try to recall, they say, I just don't know. So you kind of like, they say don't know about, it's about everything. It's too overwhelming. What do you not know? What is, you have this, you have just guessing, and you have knowledge, and between them you have intuition. Intuition is unconscious realization that something is true, but you have to bring it to consciousness. That's how you know something is true. Good? So the derivative of the inverse, it's simply this, right? If I want to calculate the derivative of f inverse at B, that simply is 1 over the derivative of f at A, where A is simply, it's simply f inverse of B. I think I forgot to put a -1 here. It should be f inverse of B. Yeah. Good. So I just obtained a formula for taking the derivative of And I'm going to actually test it now. Okay, so it's a bit tasking. I will do it in several ways, and some way it's more mechanical, but this way is good to build your imagination. You have to understand your goal is not to pass this class, which is very trivial, even if you get it with A plus. Your goal is, I'm hoping, to improve your thinking, right? And to improve your thinking is hard. You have to really task your imagination. Here is my question. Are you ready for it? So let me maybe show you first how I do it geometrically, and then I will give you a question, right? So suppose that I asked you to take the derivative. You know how to do it already, actually, but suppose for the humor, you are interested in taking the derivative of the cube root of x. Yes? With me? The cube root of x. So I can imagine drawing the graph. So this is x, this is y, and cube root of x doesn't matter how it looks like exactly, but something like this. You actually don't need to draw the actual graph. You just have to draw maybe something that helps you. Okay. So then what do I observe? So the cube root of x means that this set of coordinates is x, the cube root of x. Another way to write this set of coordinates is, of course, to say that in other words, this is saying that the second coordinate is the cube root of the first coordinate. Another way to say the same thing is to say, if the second coordinate is y, then the first coordinate is the cube of y. You understand what I did? So then, if I stand in some position x, the corresponding point is y equal to the cube root of x. Now, I know how to take the derivative of y cubed. So I can imagine placing an astronaut on the y-axis. And he sees, let's say, he sees this. This is this tangent line. This is this tangent line. And he will measure his horizontal will be a dy. And his vertical would be a dx. So if you measure dx over dy of the curve, because what is this curve? This curve is y cubed, is 3y squared. And so the other guy, this guy on the x-axis, I need to find the derivative of cube root of x. He will measure a slope 1 over 3y squared. But at what y? Y is equal to this number. So the solution is 1 over the cube root of x times 3, and the number is squared. You see, I just figured out how to take the derivative of the cube root using simply geometry. Do you understand what I did? Because I recognized it's really the derivative of y cubed, but y cubed, and then that's the slope calculated when the y-axis is the horizontal. And to convert to y-axis being vertical, I just take the slope and I write 1 over it. You understand, guys? I mean, you might think, well, I have other ways of calculating this derivative. That's great. I'm just trying to train your imagination to see this, right? So it's not really just for this purpose. Do you see how I can just flip the slope? I have here 1 over the slope calculated where y-axis is the horizontal, because 1 over that slope is the slope calculated by the astronaut walking on the x-axis. Right? And that's the slope I asked to calculate when I say find the derivative of the cube root of x, right? And then I just and at what point did I have to calculate the slope on the y-axis? At the point where y equals to the cube root of x. So I just showed you that the derivative of the cube function is really the same in a sense as the derivative of the cube root. Good. Cube root and cube are very much the same. Let's see if you understand it. Okay. Now you're going to try to derive a formula that maybe you have not seen before. Are you ready? Ask me questions if you still need some elaboration, because I'm going to give you a question like this and see if you can think geometrically. No? No questions, or you're so confused that you have no idea what to ask? No, good. Let's hope not. All right, so don't be too discouraged. Just here is the question, right? I want you, do you know what is ln of x? That's simply log base e of x. And of course, you see that e to the ln x is x. So they are inverses of one another, yes? Clear? So they're inverses of one another. I want you to tell me what is the derivative ddx of ln x. See if you can figure that out. Using geometry, right? I want to see if you can figure it out using the geometry. You can do it. All right, one person did it. What about the rest? I hope did it correctly. I mean, the idea, not just because you saw it before. How can it be zero? Zero means that zero means that this is a horizontal curve, a horizontal line. When you say slope is identically equal to zero everywhere, you're saying you're just seeing a horizontal line. Okay, yes, but the question is, of course, how do you get to this answer? You can Google it. That's one way to get it. All right, I'll wait another 2 minutes and then we'll talk about it. All right. Let's imagine what happens here. So we have the y-axis and we have the x-axis. What is ln x? ln x is a curve that looks something like this. It doesn't matter, by the way, how it looks like. It's not part of the solution. It just, the coordinates are x, ln x. That means that if I select a point x and I place an observer at this point, the observer looking up will see that the corresponding altitude is ln x. Now I can set ln x equal to y. So that means that an observer staring from the y-axis at this position, he observes x. Good? He observes x. So this is the tangent line that they both see. They see the same tangent line. Yes? You see, guys, you say you understand, but if you understand, then you can solve it. Why haven't I seen a lot of solutions, right? They are seeing the same tangent line. Now, what's the relationship between x ln x and if I call this coordinate? So if he's looking at it as y, then he's going to see what coordinate? He's going to see the coordinate y here. And what is the altitude coordinate that this guy is seeing? So he's seeing y. And what's the altitude coordinate? The altitude coordinate is the coordinate of the x-axis. What altitude coordinate will the astronaut on the y-axis see? Help me. His horizontal coordinate is some position y. What altitude does he see? The astronaut on the x-axis, he looks at an arbitrary coordinate x and he sees altitude ln x. A guy standing on the y-axis sees no x and not 1 over x. What altitude will the astronaut on the y-axis see? If this is y, how do I get x from ln x? You have to recall that e to the ln x equal to x. So when ln x is my y here, right? So that it be e to the y equals to x. So he sees the exponential function. This guy on the y-axis is just seeing the exponential function. Is it clear? Because e to the ln x is x, and that's my y here. So it's the exponential function, e to the y. I will explain this another way that is less, how do you say, less geometric, but perhaps more, well, you would more easily be able to carry out calculations, but without kind of blindly, right? So then I'm going to calculate the slope of this point. Didn't get what, Muhammad? What would you like me to repeat here? You see, what confuses you, one of the things that might confuse you is x, y, but I don't think x or y. I think the guy here on this axis, what is his horizontal position and what is his vertical position? For him, this axis, from our perspective, it looks vertical. We agree on horizontal with astronaut that is here, right? That is on the x-axis. Okay. For the other astronaut, the y-axis is the horizontal. And the question is, what does he see? If the guy on the x-axis is x ln x, the guy on the y-axis is going to see e to the y. Why? Because again, look at it. Pick this point. Pick this point. What's the relationship between x and y? Is that y equals to ln x. So if I take e to the y, I'll get x. Right? Look at it. Ln of x is the thing that you place over e to get x. So he will see e to the y. Are you with me? So then the slope that this guy will calculate. Let me have this drawn. So this guy will calculate this slope. So that's his that's the dy, that's the dy, and this is the dx. So the vertical astronaut, this astronaut, will calculate that the slope is dx over dy, and that's simply equal to e to the y. That's the slope that he calculates. But what is e to the y? It's e to the ln x. So in terms of x, he calculates the slope to be equal to x in terms of this x-axis. And so he thinks the slope is the x position of the other astronaut, right? It's the same as where the astronaut is located. And therefore, this astronaut realizes that the slope realizes that his slope, if this one calculated the slope to be x, he realizes that his slope is dy over dx equal to 1 over x. So it follows from this calculation that the derivative of ln x equal to 1 over x. Done. Do you understand? You say you understand, some of you, but then why don't you calculate it yourself? Okay, so let's we will see that done several times. Let's continue with, yeah, I'm waiting. You can write, but it's also in the lectures there. I will explain it another way that's a bit easier to calculate. You might get the other way more, but the thing is, what is it that you're getting? You see, it's not only this question that you're trying to solve. It's a sort of insight that I'm hoping that you will have. So how many of you have understood the explanation, you think? Could you please text maybe say why you understood? I will show you other ways to do that abstractly, but all right, let's continue. All right, guys. Here is your exercise. Can you figure out, using the operations that I just described, what's the derivative of, we already did x cubed, you can figure out what's the root. Let maybe do the fifth root. Can you calculate the derivative of the fifth root using this idea? I'll show you other ways of doing that in a moment. So I would like you to calculate the derivative of the fifth root of x using that geometric idea to see if you get it. Try to do it fast. You are hearing the desperate screams, are you? Okay, Alexa, let's see. So x fifth root of x, then is it, but not to the power of minus 4 over 5, right? Be careful. So the graph, you're skipping a step. The graph of the other thing is what? So you see, the guy on the x-axis is reporting altitude root 5 of x, of the first coordinate, right? So then the guy on the y-axis will report what? Altitude. We'll do it in a moment. Okay, just think about it. Well, sure, but what exactly is the relationship between the coordinates, right? If you consider the y-axis as your horizontal, what is your altitude? Sure, what's the vertical for the person walking on the y-axis? What's the coordinate? Okay. It's okay, I will show you in a moment. All right. I suppose let's do it together if that's the situation. All right, so let's do it first. Here is a simpler way to calculate it, but not insightful perhaps, okay? So let y equal to the cube root, or not cube root, I think fifth root, yes? Fifth root of x. Good? Then y is implicitly, I can write y cubed equal to x. Do you agree? I just cube both sides. I have y cubed. Again, my apologies. Y to the power of 5. Yeah? Are you with me? And then I can use implicit differentiation. Look at it. The derivative of y to the power of 5 is equal to the derivative of x, which is 1. But what's the derivative of y to the 5? It's 5 y to the 4 dy dx. Here is dy dx is the derivative that I'm interested in. And that's equal to 1. So that means that dy dx equals to 1 divided by 5y to the 4. And then what is y? It's this thing. So it would be 1 divided by 5, the fifth root of x to the power of 4. And you can, of course, write it as 1 over 5, x to the power of minus 4 over 5. Yes? So I did it using implicit differentiation. You might, of course, let's see if you can do it with some other functions quicker. You might, of course, then wonder, what's that geometric thing about? You made everything very difficult. Of course I have. I'm trying to get you to see it. What is this one about, right? I'm not just trying to get you to answer those calculus questions, which are, of themselves not interesting. So here is another example, guys. Can you please find the derivative of log base 3 of x? You can use it using the implicit differentiation idea. And we can afterwards, again, if you want in office hours, train the geometric way of thinking about it. You understand? The geometric, you saw the 1 over. Why was it 1 over truly? And how did you know that the function is differentiable? That you have all those questions. You see, geometrically, I obviously know the function is differentiable because I'm looking at the graph that's made of line segments. I know that from the inverse function being differentiable. I mean, from the original function is differentiable, then the inverse function is just built up of it's a curve built up of the same line segments, but the slopes are 1 over. Yes? So geometry gives you, I think, a simple insight. All right, so calculate this derivative. You can use implicit differentiation if you'd like. Hint, you just begin by saying y equal to log base 3 of x. That will help you start the problem. The cat is in prison. If anyone really wants to see him, I can show you. Otherwise, I'll let him go. Okay. Yeah. Yes, it's a very nice. I have two of them, right? So pretty. Which one do you prefer? Oh. Mm. Very good, Alexa. Very good. Excellent. Excellent. Amazing. Okay. So we will do it using implicit differentiation this moment because I think you will find it easier. But easier again, you see, your goal is not just an answer. Your goal is, I'm hoping, is vision, right? So you might be blind and you might kind of feel your way in the room, but you do not see how beautiful that room is. Doesn't matter that you walk through the hallway. Come on, guys. One person finished. What about the rest of you? All right. Come on, guys. So what's going on? Why only one answer? Okay, two. Come on, don't fall asleep. Fast. Okay, so far 4 people out of I see people abandon me. 25 here. Okay. Six people. All right, let's do it together. I'm not sure how many of you are even here anymore, right? My God, should be fast. So what do we have here? Look at it. If I take 3 to the power of log base 3 of x, right, I will get x. So that means that 3 to the power of y equals to x. Are you with me? 3 to the power of y equals x. Now I can use implicit differentiation. So that means that the derivative would be 3 to the y, ln 3, that's the derivative of 3 to something, times dy dx equal to derivative of x, which is 1. Do you follow the step? Yes. And so what I have is that dy dx equal to 1 over 3 to the y ln of 3. But what is 3 to the y? 3 to the y, I see here, is x. So the answer is 1 over x ln 3. Again, guys, I showed you using implicit differentiation this time because geometrically great, Alex. I'm really proud of you, right? First to do it, amazing. Right, but again, guys, this just because what I did now is perhaps simpler than what I was doing with the geometry, that does not preclude the geometry, because that is just do you have the visual, do you have the insight? Good. How, by the way, goes my exam? Online tutors working hard to solve it for you? Again, if you have questions in office hours, I can give you similar problems. I'll help you solve it. Just relax. Focus especially on the final, because the final no one will help. It is out of my hands. No mother goose like me. All right, guys. So here is your next task, okay? We know how to calculate the derivative of any logarithm, right? So you can easily infer. I hope you can infer. Actually, do it very fast. Do this. Take the derivative of log base a of x. What's the derivative? Tell me the formula as fast as you possibly can. for any derivative of logarithm? Well, David, you're making a small mistake. Yes, Alexa. Yes. Yes, Yuzu, and onwards. So the derivative, how do I solve it? Here is the small trick, is that again, I can say y equal to, yes, Zainab, y equal to log base ax means that if I take a to the power of y, I will get a to the power of log base ax, and that will be x. You agree? Because a raised to the power that a needs to be raised by to get x, that's what this is saying, is x. So then by implicit differentiation, the derivative of a to any power is a to any power ln a times dy dx, which is 1. And so dy over dx equals to equals to 1 over ay ln a, but a of y in terms of x is simply x, so it's 1 over x ln a. Good. So now please, as quickly as you can, I mean, we're wasting a lot of time here, what is the derivatives of the functions in a? So calculate derivative for a, please, very fast.
Добрий вечір, Arkady. Я снова дома. Работа была очень утомительной. Вчера я работал 16 часов. Я в отпуске с понедельника. Надеюсь, ты что понял? Ты что-то понял?
I'm sorry I didn't mute it, guys. Did anybody hear what was going on there in my phone? Do you know why I didn't mute it? Let me tell you why. That is my German policeman, right? Which I might actually ask him to use German department to investigate your exams, right? That's what my intention is. I'm teaching him Russian, so I want to forward it to the German department to check whether you're cheating on your exams. Exactly, right? Yes, Alexa, I'm a little this, right? But I think you will enjoy it. Yes, Lakey, that's exactly what it means.
Большое спасибо. Как дела?
Come on, guys, fast. Come on, guys, don't die. You're not. I know it's winter, and in the winter, cold-blooded reptiles cannot move. But come on, warm up. Take in the sun and write the solution fast. All right. What's the solution for A? The derivative of ln is 1 over whatever is inside. So it's 1 over x squared plus sine x times the derivative of x squared sine x. It's 2x plus cosine x. Are you with me? Yes? Come on, now you are solving problem B. Fast, problem B. Alexa, B, see, whenever you say derivative is identically equal to 0, that means that you're seeing a horizontal line. So be very careful there, right? If you're seeing a horizontal line, can it be a horizontal line? That's the thing. Okay, Kirill? Come on, guys, last push.
Arkady, Etkin, Poratoro, Purnara, Pustora,
Professor, you're on mute.
Thank you. Thank you. Good. I suppose on mute I'm much better, right? You don't listen anyhow. How do you solve b? Let's solve this together, guys. Derivative of 5 log base 3x plus x equal to 5 the power ln 5 times the derivative of the power, which is 1 over x ln 3 plus 1. Are you with me? Please confirm that you are here, or that you understand something, or that you're doing this work here. I want to see some messages here. Here in spirit as well, right? So that you understand what I'm talking about. How did I get this? Well, what's the derivative? So let's just see for a moment. Very simply, right? What are the derivatives of, what's the derivative of 5 to the x? That is 5 to the x ln 5, yes? What's the derivative of any log base ax? That would be 1 over x natural logarithm of a. Always you return to the natural logarithm. You see that? Natural logarithm is special, definitely, when it comes to derivatives. Good. And so what do we get in the original question? In the original question, we have 5 log 3x plus x. So that's the power. So I take the derivative of the outer function, which is 5 to the power multiplied by ln 5. That's the derivative of the outer function. Then I multiply by the derivative of the inner function. The derivative of the inner function is 1 over x ln 3. That's the derivative of logarithm plus 1. Clear? Yes. Good. Good. Now calculate the derivative for c, please. C. All right, Kirill. So yes, you can use quotient rule and whatnot. All right, let's do it together. So here is the situation. We can take quotient rule. We square the denominator, multiply by the denominator, and take the derivative of the numerator, yes? Derivative of the numerator is, what is that? It is 3x ln 5 and times 3. You all see that? Minus, I take the derivative of the denominator, which is 1 over 5x ln 3 multiplied by 5, because the derivative of 5x is 5, times log base 3 of 5x. I think there is an error here. It should be log base 5 of 3x. That's a mistake here. It should be log base 5 of 3x. All right. And then finally, problem number D. Please solve it. Yes, Kirill. So what is this thing? Did I, by the way, I forgot for this class, did I show you what was happening in Germany or not? No? Do you want to see? I mean, this guy returned very tired from suppressing civil rights. Yes, I can show you what he was doing there. They passed now a new law in Germany where you can go into someone's house without a search warrant. Yeah, so let me show you the solution to this problem. Problem number D. The derivative of log base 10 of e to the 5 e to the x is what? Derivative of logarithm is, by the way, you see how I can easily do this problem. Instead of taking the derivatives right away, I can drop the 5. Look, here's what I can do. I can drop the 5e to the x and bring it here. And so now it's the derivative of log base 10 of e is just a constant. So it's just the derivative of 5e to the x. So the answer is 5e to the x ln base 10 of e. That's the simplest way to solve it. You can use properties of logarithm to make your life easier if you want to. Yeah. So yes, that concludes this lecture. If you misunderstand something, or again, mornings are not my thing, you can always visit the evening section where it's a lot more fun. I think more people are participating. I'm not sure exactly how that works, and stay forever after class, like an hour and a half. I have a group of 7 or 10 people that stay after class all the time. If you want, we can do something in office hours if you have any questions regarding exam or regarding this material. And other than that, I wish you goodbye, good night, or good morning.